what we're going to talk about is kind of the ramifications of the resulting Lewis dot structures that we've been finding. Okay, so we are hopefully able to draw Lewis dot structures for compounds. Now, we want the Lewis dot structures for these compounds to tell us the shapes of these molecules, because the resulting shapes tells us a lot about the properties of the molecules. Okay, and that's why the Lewis dot structures are powerful and useful the way that they are. So the first thing that we need to know to recognize the shape of the molecule is we need to know that there's a relationship between the shape and the regions of electron density around the central atom. Okay, and this is true for extended molecules as well, but everything that we're dealing with are just small molecules with a central atom and ligands. Sometimes we have hydrogens coming off of oxygens and in oxyacids. But for now, if we take a look at this compound here, CH4, we can see that there's 4 regions of electron density coming off of the central carbon there. Okay, and that 4 regions of electron density is important for identifying, again, the shape and the resulting properties then of the molecule. Water here, our central atom is oxygen, and we also see 4 regions of electron density. However, 2 of these regions are non-bonding regions, while 2 are bonding regions. But there's still 4 regions of electron density. Okay? Now, let's bring out an image of what happens when we get 4 regions of electron density around a central atom. Okay? So, there's this website online called MolView, I guess. It's nice and easy to use, and if I make this compound a carbon and bring one more off there, and then sweep up the shape and then convert it and see the 3-dimensional shape, what I can see here is what it looks like when there's a carbon that has 4 hydrogens around it. Okay? Now, if I were to draw this off to the side here, carbon with 4 hydrogens around it, I would draw it like that. That would be my Lewis dot structure. And I might think, oh, the angle between these 2 hydrogens, because of the way I've drawn it, is 90 degrees. Okay? But that's not the case because our molecules are in 3 dimensions. They're not confined to the 2 dimensions of our drawing here. Okay? So this molecule in 3 dimensions shows that the angle between the ligands on this carbon here are not 90 degrees, and it might not be intuitive what the angles are. Okay? If I look at something like this compound here, where there's a central atom and only 3 regions of electron density, right? Central atom X, 3 regions of electron density. Okay? Based on what the drawing shows us here, we might be able to predict what that angle is. Harry, what do you think? What does it look like that angle might be? Any ideas, Harry? What do you think that angle might be?
It looks like 120 degrees.
120 degrees. Very good. Now we should maybe have a quick review about our degrees. For example, a circle, right, is 360 degrees, right? Halfway around the circle is 180 degrees, right? Okay, going all the way around is 360 degrees. You've heard the joke before, or maybe you haven't, but the football player who says, we got to turn this team around 360 degrees. Now, we only pick on football because this actually happened, I guess, you know, in football or whatever. But anyways, why is that a funny joke, Catherine?
Before they were?
Yeah, that's right. Going around 360 degrees is going back the same direction that you were. So I just tell you that joke to help you remember 360 degrees is a circle. And if you're a exercise sports science, you just say we're going to turn the team around 180 degrees, right? That's the appropriate thing to say to encourage your your fans or your team or whatever. Okay, so like Harry noted, if you have one central atom and 3 ligands, then the angle between those atoms is 120 degrees, okay? And this angle here, although we can look at it and think, oh, maybe that's 100 or 90 degrees, we know now that it's not 90 degrees because in 3 dimensions, the atoms can spread out more. Now, this value is, and you're just going to have to know this number, is 109.5 degrees. 109.5 degrees. And we can tell that angle simply by the regions of electron density that are around the central atom. So, for example, here, water molecule here, this water molecule. Katie Thomas, how many regions of electron density are there around this oxygen in this water molecule?
I'm not sure, but I'm going to guess 6.
Okay, the regions of electron density is identified by the bonding regions. So there's one bonding region here, one bonding region here, 2, and then this non-bonding region is a 3rd, and then this non-bonding region is a 4th. All right, so we have 4 regions around there. Does that make sense, Katie? Okay,
Yeah.
very good. So then, Landon, if we have 4 regions of electron density and all those regions try to get as far away from possible as each other as possible, then what is the angle between these 4 regions of electron density on this molecule, Landon? What's the angle between, let's say, these 2 hydrogen-oxygen bonds in water?
I'd say 90 degrees.
Okay, it's actually 109.5, or a little, right? Because there's 4 regions of electron density, and those 4 regions of electron density spread out like this when we're in 3 dimensions. Okay, now, here's a compound, carbon dioxide. Nikki, how many regions of electron density are around that central atom?
Does a double bond count as one region?
It does. It only counts as 1 region.
Okay, so then there's 6.
No, there's only, around this central atom right here, around the carbon,
Oh, then there's 2.
yeah, 2. 2 regions of electron density. 1 here and 1 there around that central atom. Very good. And then we can imagine 2 regions of electron density trying to get as far away as possible from each other. And we can see that the angle between the carbon-oxygen bond, what would it be, Nikki?
Would be a 180.
180 degrees. That's right. All right. So, if we want to know the angle between the regions of electron density, or in the end we'll see how this affects the actual shape of the molecule, what we need to do is just count the regions of electron density around the central atom. All right, let's go to this one, and Samantha's going to answer this question for us. How many regions of electron density are around the central atom in this species right here, Samantha?
5.
That's right. There's the central atom, and we got 1, 2, 3 non-bonding regions, and 4, 5, 2 of the bonding regions, so a total of 5 regions altogether. Taewon, how many regions of electron density are around the central atom in ammonia, NH3? How many regions of electron density are around the central atom in ammonia, Taewon?
It is 4.
4, that's right. So Taewon, what would you say the angle is between this nitrogen-hydrogen and this nitrogen-hydrogen in this compound?
It is 109.5.
Very good.
degrees.
Very good. Even though on the way it's drawn, it might look like 90 degrees, it's not the drawing that we're taking the information from, it's the regions of electron density, right? The number of regions of electron density tells us that angle there. Okay, very good. So let's take a look at these different shapes that can result upon having different number of regions of electron density around the central atom. As we said, yeah, go ahead.
So instead of an angle being 90 degrees for the carbon with the 4 hydrogen around it,
Mm-hmm.
is it supposed to equal 360 or not?
No.
Because if it was 9.5 for each angle, then it would be more than 360, right?
Yeah, but that's all right because we're not asking how many angles are necessary to get around a circle here, right? Because this isn't a circle. This is in 3 dimensions. This thing's coming out right at us. These ones are going away from us, and this one's in the plane, right? So we use the circle when we know everything is in the same plane. Then we can use the circle, the 360 degrees, to make an estimate of what the angles would be.
Okay.
So 2 regions of electron density forms a linear compound, right? Central atom, 2 regions of electron density that are going to try to get as far away from each other. You have a linear compound. 3 regions of electron density, right? We have all of these atoms are in the same plane. Let's take a look at again at what this looks like. All of these atoms are in the same plane, central atom, right? And we need a name for this, okay? Now, I know that most of you would want to call it Fred, but that's not an appropriate name because that doesn't remind us of the actual shape. So instead, what we're going to call it is we're going to call it a trigonal because it's triangular in shape, and we're going to say it's planar because all of these atoms are in the same plane. So we call this a trigonal planar molecule. So here's an example of a trigonal planar molecule when we have a central atom, 3 regions of electron density. Central atom with 4 regions of electron density, this shape is called, now they could probably have come up with a better name, I don't know, but because here we're calling it, well anyways, it seems to break the rules, but this is called a tetrahedral. Tetrahedral. Now the term tetra, do you know where that comes from, Harry?
Isn't tetra the prefix for 4?
Yeah, that's right. And that's 4, and you can think of it as 4 things being bound to it, but it's actually because of the 4-sided, because tetrahedral, hedral means sided. So this is a 4-sided structure that you'd see here, right? Okay, very good. Now, if we take a central atom and put 5 regions of electron density around it, you get something different happening. So let's look at this molecule really quick. Central atom, 5 regions of electron density. So what do we want here? We want a central atom there, 5 regions of electron density. 1, 2, 3, 4, 5. 5 regions of electron density. The resulting shape that you get is a little bit different, all right? What we see here is if we were to imagine this as a molecule that's kind of shaping out the shape of a sphere, like a globe, we see 2 atoms in axial positions, right? And this one here, you can see it has neighbors that are 90 degrees from it. 3 of these neighbors are 90 degrees and one's 180 degrees. Same with this other axial atom, has the same conditions. But we have these 3 other atoms which are in what we would call the equatorial positions. Because if you thought of this as a globe spinning like this, these would be along the equator. And the equatorial atoms have different relationships with their neighbors. This equatorial atom, for example, has 2 atoms that are in the axial positions, 2 that are 90 degrees away from it, but 2 others that are 120 degrees away from it. All right? So again, central atom, 5 regions of electron density, we get this shape. Now we're going to call this shape based on the fact that the top looks like a pyramid. If you connect all the dots in the top, the equatorial dots in the top, it looks like a pyramid. Also, if you connect all the equatorial dots in the bottom, it looks like a pyramid. And this is a triangular shaped pyramid. We call this trigonal bipyramidal. Trigonal bipyramidal. Okay? So if we have 1 region of electron density, or sorry, 1 central atom and 5 regions of electron density, the shape is called trigonal bipyramidal. All right? If we have a central atom with 6 regions of electron density. The resulting shape should have been called square bipyramidal, but instead they call it octahedral. Octahedral. Octa meaning 8, and if you look at this, a drawing of this kind of a molecule, central atom, 2 electrons along the y plane, 2 electrons, but 2 bonding units along the x and y plane, and then 2 along the z plane, right? If you look at this structure, you see that it would have, if it was a die, it would have a total of 8 faces. 8 faces along here. Okay? So that's where our octa in octahedral comes from. All right. Very good. So we got linear. We got this thing here. What do we call this thing, James Oliver? What is this thing called?
I'm not sure.
Okay. It's what shape?
Said tetrahedral?
No, there's 3 regions, so it's like a triangle here. Do you see that, how it looks like a triangle? And because there's only the 3 regions, it's in the same plane. So this would be called trigonal planar. We call that trigonal planar. How about this one, Catherine? Do you remember the name for this thing?
Try something.
This one should be named try something because it is a nice triangular. It should be called trigonal pyramidal. But it's not. It's called tetra something because of the 4 sides that the resulting shape has. Do you remember what it's called?
Oh, tetrahedral?
Tetrahedral. Tetrahedral. Very good. All right, Katie Thomas, what do we call this one here? 1 central atom, 5 regions of electron density. What shape does it take?
I can't remember.
Okay, it has to do with the top looking like a triangular pyramid and the bottom looking like a triangular pyramid. So it's trigonal bipyramidal. Trigonal bipyramidal. And Landon, what is this last one called here? 6 regions of electron density around a central atom?
Octahedral.
Octahedral. Very good. Now, and these next slides talk about these different shapes. Now, another thing that we have to think about here is the space. So the reason why you get these resulting shapes is because all of the regions of electron density want to be as far away as possible from the central atom. And this theory, or this idea, is called the Vesper theory, or Vesper model, which is talking about the valence shell electron pair repulsion theory. These electrons try to get as far away from each other as possible, and so the resulting structures are found. Now, if you, instead of 4 bonding regions, in the case of tetrahedral, for example, if one of your regions is non-bonding, okay, then the non-bonding region ends up taking a little more space than the bonding region. And that's because you can imagine 2 nuclei being in a bonding condition. The electron density, as it strays from one nucleus, begins to be attracted to the other nucleus. However, in a non-bonding region, electron density strays from the nucleus, and then the only nucleus it has to come back to is that initial nucleus. And so you get a larger space being taken up by non-bonding electrons. All right? So what that means is that when there's non-bonding electrons, the other bonding atoms actually get squeezed a little bit closer because these non-bonding electrons take up more space. All right. So, Nicole, your turn. We have how many regions of electron density around this central atom here?
You have 4.
4, that's right. 1 non-bonding here, 1 non-bonding here, 1 bonding, and then this last one's 4th one bonding there. So what would the shape of those 4 regions of electron density obtain? What do we call that shape?
It would be tetrahedral.
Tetrahedral, that's right. And the angle between these XM bonds, what would that angle be?
They would be 109.5.
That's right, 109.5. Very good. Now, in fact, we would say it's a little bit less than 109.5. And that's what we say, a little bit less. Why do we say it's a little bit less than 109.5, Nikki?
Me?
Yeah.
Because the other ones are not there, so they have more space, or they get squeezed together.
That's right. These 2 non-bonding regions take up more space, squeezing the bonding regions closer together. All right. Also, we now can differentiate between what we call the molecular shape and the shape of the electron domains. So there's 4 regions in all 3 of these molecules here. There's 4 regions of electron density. However, in these bottom 2, regions of the electron density are taken up by non-bonding regions, as opposed to up here at the top, all bonding regions. Okay? So that makes a difference between the shape of all of the electron domains and the resulting shape of the molecule itself. Okay? So let's take a look at this sort of a thing. Well, we can go back to this slide here and look at that. Here is 4 regions of electron density around a central atom, and water is also in a scenario of 4 regions of electron density around the central atom. However, the actual molecular shape of these differ, right? The regions of electron density are the same, and so you have water, central atom, bonding hydrogen, non-bonding electrons. In CH4, right, 4 regions of electron density. So the angles between these are pretty similar. These non-bonding squeeze these in just a little bit, but it's very close to 109.5. However, the resulting shape of the molecule is different, we say, because this doesn't really there's no bonding, no atoms over there, so the shape of the molecule is slightly different. This one, we say, is tetrahedral. Tetrahedral, H-Y-D-R-A-L, tetrahedral. But this one here is not, the molecule is not tetrahedral. The regions of electron density obtain a tetrahedral shape, but the resulting molecule is only what we're seeing here in this section. So if you drew it without anything, if you just drew the atoms themselves, it would look like this, right? And that shape here, that shape is what we call bent. All right? A linear molecule that's been bent is called a bent molecule. Okay, so we have examples where we have similar or the same number of regions of electron density around a central atom, but the resulting molecule is a different shape. Okay? Tell me, somebody, what you think. Taewon, you can answer this question. What is the shape of this molecule? It's a central atom with 3 regions of electron density, but 2 are bonding and 1 is non-bonding. So what's the shape of this? What would we call the molecular shape, Taewon? What would you call the molecular shape for this compound?
Triangular, backplanar.
Okay. trigonal planar would be the shape of, not the molecule, but the shape of the regions of electron density. Because there's 1, 2, 3 regions of electron density. But the shape of the molecule, any ideas, Harry? What do you think the shape of the molecule would be?
Is it bent?
It's bent. It's bent. Now, water is another example of a bent molecule. We just saw that, right? And water, we had an angle of about 109.5, a little less. But this is a bent molecule with an angle of, what do you think, James Oliver? What would the angle be in this bent molecule?
Would it be 109.5?
Well, no. In this one here, our angle is a little closer to, what do you think, Catherine? We count the number of regions. 1, 2, 3. What do you say?
Would it be 120?
That's right. Good job, James. So 120 degrees there. It's a bent molecule. The shape is bent, but the angle is 120, whereas water's shape is bent, but the angle is a little less than 109.5. Okay. So we have different shapes of molecules that result based on the number of regions of bonding and non-bonding electron density. Okay. So Katie Thomas, let's see if you can remember what the name of this molecule's shape is right here. Can you remember, Katie?
That one was trigonal bipyramidal.
Very good. Trigonal bipyramidal. All right. Now, notice that if you replace bonding regions with non-bonding regions, those non-bonding regions go on the equatorial locations of a trigonal bipyramidal compound. And that's because the equatorial regions have more space. If you put non-bonding regions on tetrahedral or non-bonding regions on octahedral, see there, it doesn't really matter where you put it. If you put it over here, I could switch this around and it could move around to any location and it would be the same in terms of the molecular structure, right? If I put it on the axial region, it would be the same as the equatorial region in terms of its actual shape and its location. But for a trigonal bipyramidal compound, replacing bonding regions with non-bonding regions requires that the bonding or the non-bonding regions take up the equatorial space. All right? Did you follow that, Landon?
Yes.
So why is it that the non-bonding regions are in the equatorial space?
Because they have more space.
They have more space there. That's correct. Very good. All right. So, Nikki, looking at this bottom one here, the shape of the regions of electron density is still trigonal bipyramidal. But what do you think the shape of the resulting compound is, the resulting molecule?
We have to pass on that one.
All right. So we have a central atom, and we have one region of electron bonding density here and another one down below. So it's a linear compound, right? A linear molecule. Can you see that?
Yeah, so then it's linear and it's trigonal bipyramidal.
The shape of the molecule is linear.
Okay.
The shape of the regions of electron density that they hold themselves in is still trigonal bipyramidal, but the shape of the molecule is linear.
So are there two names for each structure, or no?
No. Usually what they're after is the molecular structure, but you can't know the molecular structure without first knowing what the shape of the regions of electron density attain. Does that make sense?
Okay. So the molecular structure of that one is just linear.
Linear. That's right.
Okay.
All right, Samantha. Knowing what we know about our molecules and names of our molecules, could you give us a hypothetical good name for this molecule right here? The shape of this molecule? Let me give you a hint.
Tetra.
This one here helps in the naming of this compound down here.
Tetraplanar.
Tetraplanar, very good, very close. Do you remember the name of this one, Samantha?
It's not.
It's
Trigonal planar.
Trigonal.
Trigonal planar, very good. This is trigonal planar, and this one down here they call square planar. Square planar. Does that make sense, Samantha? Can you see why they would call it that?
Yes.
Very good. How about this one here? Anybody think they might have a good name for this compound right here? The shape of that compound, sorry. This is a, nobody? This is a pyramid, that's right. It's a pyramid. And instead of calling it a trigonal pyramid, what do we call it, Landon? What do you think?
I'm going to say pyramidal planar.
Okay, it's a square. It's a square pyramid, a square. So it's a pyramid with a square base. All right, just like this one was called trigonal pyramid, but there's two of them, so it's trigonal bipyramidal. This one is called square pyramid. All right, and then there's one more here. Harry, what do you think this one will be called here? The shape of this compound.
Is that trigonal planar?
Okay, they're not quite in a plane, right? Because this region of electron density is pushing these ones down. But it is called a trigonal pyramid. It's a shallow pyramid, but it is a pyramid where this is the top and these are the bottoms. Can you see that?
Yeah.
Excellent. All right, so then what this information then requires of us is to be able to answer this kind of a question here. And what we're answering, this one here, is what's the molecular geometry. So we want to know the molecular shape of SO2. All right, so Taewon, you want to help me with this one? What's the molecular shape of SO2? We first need to draw SO2, right? We need to draw this compound, Taewon. You want to help me draw it? You ready, Taewon? You ready to draw the molecular or the Lewis dot structure for SO2? Let's see, was there 18 electrons to start off with?
Yeah.
Okay, so now we have 16 electrons out there. Okay, good.
Um, uh,
Are you thinking you're done, Taewon?
I think I
Okay. Anybody see any issues with that structure? Does everybody agree? Oh, so you're putting some more electrons on there? Yeah, we didn't have enough electrons, did we? Okay, now we have 18 electrons on there. Very good. How about formal charges? Are there any formal charges left, Taewon?
I think it's all 0.
Yeah, that's right. All three are 0. Very good. So, Taewon and everybody, think about it. What is the shape of this molecule? What's the shape of this molecule? To answer that, we first need to recognize the number of regions of electron density. Think about how those regions would try to separate themselves. Look at how many are lone pairs or bonding sets, and then identify the shape of the molecule. Let's see. James Oliver, can you think of what do you think would be the shape of this molecule? Let's go back to my screen
I
here.
feel like the shape would be bent.
Bent?
Yeah.
That's right. Bent is right. Very good. So, it's bent because the 3 regions of electron density would cause these 2 oxygens to bend down, and we'd have a non-bonding region right there. And, Catherine, what might we predict is the angle between these 2 oxygens?
120?
Yeah, that's right. 120. And with this lone pair here, we might predict that it's a little bit less than 120. And why is that, Catherine? Why would we predict a little less than 120 with the lone pair?
Because the lone pair takes more space.
That's right. Takes up more space. Very good. Excellent. So, here are some other, and this slide contains all these different names for you to kind of become familiar with. This shape right here, trigonal bipyramidal, 2 regions of non-bonding density, is called a T shape. Trigonal bipyramidal, 1 region of non-bonding electron density, is called a distorted tetrahedral or a seesaw, like a teeter-totter. I don't know if you guys remember that as kids. All right, so octahedral geometries. We talked about this one, square pyramid. This one, square planar. Very good. So, here's a good one. Where are we at? Katie Thomas. What is the name of the shape of ammonia, NH3? What's the shape of an ammonia molecule? While you're thinking about that, Katie, here is the Lewis dot structure. But if they just said, what's the shape of ammonia, NH3, it would be hard to know unless you drew the Lewis dot structure and saw that there were region of lone pair electrons. So recognize that when you're asked about the shape of a compound, it's the Lewis dot structure that's going to help you. It's being able to recognize, after you've drawn the Lewis dot structure, the number of regions of electron density around the central atom, and then looking at regions of non-bonding. So do you remember, Katie, what do you call the shape of a molecule that has 4 regions of electron density, 1 of them non-bonding?
I can't remember.
Okay, all right. And really, we don't want to find ourselves in a situation where we kind of have to have all of these memorized, right? We want to hopefully find ourselves in a situation where we can draw the structure on paper, right? So 3 regions of bonding density and 1 region of non-bonding. So after I've drawn this, I can, in my own mind at least, and hopefully you can too at some point, is recognize there's 4 regions. So it's taking up a tetrahedral shape, but the resulting compound that's not the non-bonding electrons would form this looks like a triangular pyramid. So trigonal pyramidal is the name of the shape of this compound here. Does that make sense, Katie?
Yeah.
Okay. Landon, what do you say? Well, let's see. What's the shape of this CH4 right here?
Tetrahedral.
Tetrahedral. Very good. Nikki, what's the shape of this compound right here?
It has. Would it be linear?
Okay. This
Or
is
bilinear?
this is drawn in a way that makes us want to say linear, right? It wants us to think that because they've drawn it this way and this is what they like to do, they want us to think that that angle is 180 degrees, right? But what is that actual angle? How do we just... What is it?
Is it bent?
It is. The shape is bent. And what's the angle between the hydrogen oxygen atom or bonds?
A little less than 109.5.
That's right. Very good. All right, Samantha, you get the hard one here. What is the resulting shape of this compound? Central atom, 5 regions of electron density. Right? What would a central atom with 5 regions of electron density look like?
That would it look like bipyramidal?
Very good. The 5 regions would be bipyramidal. So 2 axial and then 3 of them in equatorial positions. And now the resulting shape of the molecule would be what?
Bent?
Almost. This is an iodine right there, apparently, central atom, right? And then this is an iodine, and that's an iodine. And what are around our equator here? What's around the equator?
Electrons.
Yes, our non-bonding pairs of electrons. So the resulting shape is what?
Linear.
Linear. Okay, very good. That's probably the hardest type of scenario that we'll be introduced to. Okay, so the angle on the hydrogen-oxygen bonds is 104.5, just in case you're wanting to know. So that's what we call a little less than 109.5. All right, and that's because lone pairs require more space. All right, let's see. Now, we have been introduced to what we call polar bonds in the previous chapter. And polar bonds, we can look at a bond and decide whether it's polar or not based on the location of the atoms in that bond, their location on the periodic table, right? Carbon-nitrogen bond. Carbon-nitrogen bond. Is the carbon-nitrogen bond polar, Taewon?
I think it is.
It is. That's right. It is polar. And where does our electron density want to end up on this bond? Towards the carbon or towards the nitrogen? Taewon, where do you think? Where does the electron density want to end up?
I don't understand the question.
So when we say a polar bond, what that term polar means is that the electron is pulled towards one of the atoms more. Where is the electron density pulled toward in this bond? Towards the carbon, or is it pulled towards the nitrogen? Did you say?
I'm not sure.
Okay. It's pulled towards the more electronegative atom. Which one's the more electronegative atom, Taewon? What's that?
Carbon?
No. Electronegativity increases as we go to the right and up on the periodic table. So fluorine is the most electronegative atom. So nitrogen and carbon, when we're comparing those, nitrogen is more electronegative. So this is going to be a slight negative charge, and this is going to be a slight positive charge. So if I were to kind of sketch the electron density, it would look something like that, with more electron density residing around the nitrogen. Okay? That's what polarity means when we're talking about bonds. And we can also have examples of not just polar bonds, but also polar molecules, where the whole molecule is polar. Okay? What this requires is a polar bond within a molecule, but then also a degree of asymmetry in the molecule. So if you have a polar bond but there's no asymmetry, then you're not going to get a polar compound. If you have asymmetry but only weakly polar bonds, then you'll only have slightly polar molecules in that compound. So, for example, here's a compound, CF4, all right? Are there polar bonds in this compound, Harry?
How to determine that?
Well, we look at the kinds of, we can draw the Lewis dot structure first, right? And just simply from the skeleton structure, I can see the kinds of bonds that exist, this carbon-fluorine bond, and then I can use the periodic table to determine if a carbon-fluorine bond is a polar bond. Is a carbon-fluorine bond a polar bond? Harry, do you know?
I don't really know how to determine if it's a polar bond or not.
Okay, so the way we determine whether it's a polar bond is simply by their location on the periodic table. Fluorine, oxygen, and nitrogen are the three electron hogs. They hold on to electron density tightly compared to everybody else. So anything that bonds with them will form a polar bond. If you have sulfur and oxygen bonding, for example, that's a polar bond. If you want to look at and compare electronegativity or electron density, how it would be distributed between two atoms like chlorine and bromine, so here's a bond between chlorine and bromine, the electron density would be leaning towards the chlorine in this bond because chlorine is higher on the periodic table. If you wanted to compare a bond between sulfur and chlorine, electron density here would be leaning towards the right because chlorine is further towards the right. Does that make sense, Harry?
Yeah.
So, is the carbon-fluorine bond a polar bond? Yes, it is a polar bond. Okay? But CF4 is a non-polar compound. Now, Harry, do you know why CF4 is a non-polar compound?
Is it because the electrons are distributed evenly?
That's right, because this is a symmetric molecule. Okay, it's a symmetric molecule. Very good. If I had this compound here, CHF3, or actually let's try it a little better, CFH3, all right, this, I could draw this, F, H, 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 all right, Catherine, what's the angle between the carbon fluorine and the carbon hydrogen there? Between those two?
9.5.
Very good, 109.5. The shape is tetrahedral. Is this compound polar or nonpolar? What's that?
Non-polar.
No, it's actually polar. It's polar. We have a polar bond. The carbon fluorine is a polar bond. And because these are hydrogens here, we have an asymmetric pole of electron density. Can you see that? Does that make sense, Catherine?
Yeah.
Okay. So we have a polar bond that is not balanced. Therefore, it results in a polar compound. Okay? All right, very good. I think that's where we have to stop. I'm going to show you a few more examples here just on the slides so that you can look at them. But water molecule, a bent molecule, polar because there's a polar bond and it's asymmetric. Ammonia, bent molecule, polar molecule because it's asymmetric. That's why ammonia is reactive, right? Water molecules can interact with lots of different ionic compounds, and that's because of its shape, right? Carbon dioxide, very non-reactive, doesn't react or interact with hardly anything, and that's because it's, even though carbon-oxygen is a polar bond, its linear or symmetric shape results in a non-polar compound. Okay, very good. So we answered a lot of questions and learned a lot about the resulting shape of a compound, the resulting bond angles based on our Lewis dot structures, and hopefully we can kind of go over this, and I'll provide some questions for us to prepare in a homework. Other than that, we have our final exam coming up on the 15th, opening hopefully 15th. I don't know what time of the day, depends on when they get me the questions, and then closed at the earliest the 18th. I think it'd probably be a good idea if everybody took it by the 18th. It might be able to be open until the 20th, but we'll see. Okay, it's going to be taken online. We're going to use Proctorio to kind of monitor whether or not we are cheating, right? So don't cheat. I'll be watching you like a hawk. Now we do want to have a little conversation about the practice quiz that I have up there for you who have never experienced Proctorio, right? It looks like, let's see, who has taken this quiz? Nobody's taken the practice quiz to help you practice with Proctorio. Now, you don't have to do that if you already have Proctorio experience, but I want you to take this quiz if you haven't had Proctorio experience, right? It's this quiz here. And again, the idea would be you take it so that you have everything ready so that when you take the final exam, you're not delayed or anything because of the Proctorio component. Okay, so what else did we want to mention? Oh yeah, just reiterate the timing of the exam. We could have a review on Monday. Would you guys come to a review like this if we had it on the 13th, Monday? Okay, so we'll have a review on Monday at 1 o'clock here, just like this. Other than that, I think that we're okay. Are there any other questions? Okay, if there's no questions, I'll see everybody who's interested in the review on Monday. And we will, or if you want to hang around and ask a private question, you can do that. Other than that,